But looking at the biology and the diversity that is alive in there, it's like being any sort of ecologist and getting to look at different systems and how they work. I think that we feel like we also become more partners with the soil when we're looking at it that closely and really getting to know the creatures that are alive in it.
Welcome to the 271st installment of Ear to the Ground, the Land Stewardship Project's podcast on family farming, regenerative agriculture, regional food systems, and local democracy. I'm Brian DeVore, editor of the Land Stewardship Letter. According to the University of Illinois, the per-ton price of anhydrous ammonia fertilizer has more than tripled since 2020. And with war currently waging in Europe, there are indications this upward trajectory in fertilizer prices will continue in the immediate future. Pile on top of that the fact that we may be reaching what's called peak phosphorus in coming decades, and it's become more evident than ever that we need to build the kind of healthy soil that generates its own fertility. Continued reliance on outside inputs to replace the nutrients being mined from our fields is simply not viable. That's why a new on-farm research project LSP is involved in is so timely. Inspired by the work of microbiologist Elaine Ingham, in recent years, farmers and others have been investigating how they can use intense composting to build the kind of soil biome that is self-sustaining and not reliant on a constant supply of chemical inputs. For example, since the summer of 2021, the Land Stewardship Project has been working with a group of farmers to research if a particularly innovative, low-labor approach to breaking down waste material can be a critical linchpin in efforts to bring the soil back to life. Through this initiative, LSP staff members have erected Johnson Sioux bioreactors on 4 farms in southeastern Minnesota and 1 farm in western Wisconsin. Invented by molecular biologist David Johnson and his wife Hui Chun Soo, over a period of 12 to 18 months, the bioreactor creates an inoculant that, when applied to soil, can jumpstart biological activity. The original recipe developed by Johnson and Sioux consists of 1/3 leaf litter, 1/3 dried cow manure, and 1/3 wood chips, which are piled into miniature silo-like structures that can be constructed from materials available at the local hardware store. Through the LSP project, which is being funded by a grant from the Minnesota Department of Agriculture's Agricultural Growth, Research, and Innovation Program, farmers are experimenting with variations on the original recipe, utilizing chicken and hog manure, for example. Most of the research on the Johnson Sioux bioreactor system has focused in areas like New Mexico, and studies show material produced by this composting system greatly increases the soil's fungal biomass, which results in, among other things, greater crop yields and more sequestration of carbon. One of the goals of the LSP initiative is to see how this system performs under replicated trials in the harsh climate of the upper Midwest. During the summer of 2021, I had the opportunity to observe bioreactors being erected on farms LSP is working with. After the composters were set up, I talked to a few of the farmers about why they were interested in this method of building soil health. Those conversations are featured on Ear to the Ground episode 266. As a follow-up to those interviews, I recently chatted with Max Kopish, a southwestern Wisconsin vegetable producer who is serving as a consultant on LSP's Johnson Sioux research. Using a microscope, Max has been examining samples of the compost being created in the bioreactors created on the 5 farms to determine how well the various recipes are doing at creating healthy fungal communities and various kinds of protozoa. In addition to the monitoring Max is doing, samples are being sent to the University of Minnesota for genomic sequencing, as well as to the Soil Food Web Laboratory in New York. During our conversation, Max provided me deep insights into how the Johnson Sioux bioreactor system works, the potential it holds for regenerative farming, and the big questions we hope this research helps answer.
The bioreactors are very unique in the world of composting because they are a static pile, and typically if you talk with any sort of composting expert, they're going to tell you that the main thing you need to do to make good compost is to turn it, and so it's very active and you're using a lot of human labor to turn the pile frequently with pitchforks or with heavy machinery. You're probably doing that every 3rd day or so for a couple weeks, and so on a backyard scale with food scraps, that's really important to keep the air in there. So a lot of backyard farmers and gardeners might be really familiar with composting, and the very keen labor that it requires. And in a commercial setting, that turning is meant to try to increase the time, or to, I guess, shorten the time that the composting process takes. So they do a lot of turns very fast. You have a lot of nitrogen material in the pile, so it gets very hot, and the oxygen kind of gets sucked right out from all the bacterial growth that's happening. And so the turning is required to replenish the oxygen supply. And the bioreactors are actually kind of the opposite of that, where they don't require any turning. All of the labor is done up front in one day, as you're kind of familiar with. You just load them into these big tubes, essentially, and you kind of have a passive airflow going on. And so it doesn't require that turning. It sits for a lot longer, so it's a little slower of a process. But yeah, that's kind of the main difference between what we're familiar with as compost and what the bioreactors offer, is just that airflow, but without having to turn.
I get a sense that we're also looking to create a different product, in that maybe with the regular composting that people are familiar with, that's going to be something you're going to put on your gardens or in your field, and it's kind of almost I don't know, this is maybe a very simplistic way to describe it, but it's like you're just adding fertilizer in a way to the system. But this is a much different, like you're trying to activate something in there. Is that correct?
That's exactly correct. The bioreactors are creating a biological inoculant. So we're not really going for a lot of nutrients or a high fertility, but we're really looking for a diversity of microorganisms, specifically fungi. A lot of our soils have been tilled a lot, or had chemical applications of fertilizer. And what that's really done is break up the fungal diversity and the fungal life in the soil, which is essential for plant growth and plant health. So the bioreactor, because it's not being turned, fosters a great environment to grow fungi. That, they grow in these long, delicate threads. So when it's just static for over a year before it's applied, it's really creating conditions for this biological diversity to flourish. So when we apply it too, we're using super small quantities, just as an inoculant. So it's kind of like taking a probiotic for your gut. It's one pill a day, and you're getting billions of microorganisms in there. Very similar.
I think that's a good analogy. Like, it's a probiotic for your gut. You are helping that soil maybe be more self-sufficient or self-perpetuating in itself, rather than you're putting this in. You have this endless thing that you have to keep adding, this input kind of thing, but you're kind of maybe triggering that biology a little bit.
Yeah, that is such a good way to put it. The fungi, especially that are in the bioreactors, they will be actually breaking down the mineral structure of your soil to make those nutrients available to plants. So you're like activating everything in the soil by adding this very small quantity of compost, and it's kind of going. Everybody always says is like going to the way nature does it naturally. The way that now we kind of think that plants originated, their original root systems could have been fungi. Like, they didn't even have roots themselves. They just relied on the fungal relationships. And that's really what we're kind of trying to get back to with this form of agriculture, where you have plants and fungi working together to extract what they need from the soil. And I hate to even use the word extract, because it's not. It's a cyclical balance where they're returning just as much as they're taking. And so that is exactly what the bioreactor is offering.
I've always been a little confused on, where it really struck me was I was at a farm last year where they were using grazing, and the farmer kept saying, I'm trying to create, they had a terrible weed problem on this farm, and he says, I'm trying to use rotational grazing and some other soil health practices to make this from a bacterial farm to a fungal farm. Can you explain why you would want that, and why those are, what's the advantage to that? That's something that kind of I've always been fascinated by, that I've never thought about. For example, a really weedy farm, it's got a lot of problems, is maybe one of the problems is it's dominated by a bacterial community, but I never really thought about that.
Yeah, this is something that Elaine Ingham has really pushed us all to think about. And when you think about the crops that we grow predominantly, corn, soybeans, even like orchards, growing apples or a lot of perennial crops, all of those are plants that evolve in ecosystems that don't have much disturbance. So in order to get, a very well-established prairie, let's say, where something like maybe an equivalent of corn may develop, you're going to need a long time without forest fires, without plows without a ton of heavy grazing. You need the soil that has kind of some time to rest. And when you have a soil that is able to rest for longer periods of time, the natural ecosystem balance of that soil tends to become more fungal. And so we see that, Elaine Ingham's classic example is looking at old growth conifer forests that are thousands of times more fungal than they are bacterial, versus maybe a freshly burned field or a freshly tilled field where all the fungi has been either broken up and kind of removed from its habitat or burnt essentially. And in those ecosystems, the bacteria, they're so much more resilient and they're so much more quick to reproduce that they will completely take hold of that soil. And then it kind of moves into the ecological concept of succession, where the plants that will come in and really thrive in that bacterially dominant soil are usually annuals that can grow very quickly. They don't invest much energy into the soil because they're really just there to set seed. As anybody who gardens or farms knows, that's what weeds are best at, creating that seed head. And that's exactly what plants that thrive in bacterial soils like to do. They don't really want to share much carbon with the soil. They're not really looking for soil partners because they're only there for a short growing season. And then you compare that to a fungally dominant soil where you're having plants like, trees that are going to live hundreds and hundreds of years. If a tree lived that long and didn't have soil partners, it would quickly, with our old concept of how the soil chemistry works, it would quickly soak up all of the nutrients that were there. So they really invest more in the soil and in making those partnerships. And fungi are just happen to be the organism that is best suited to make friends with plants. The way that the root systems and the fungi connect is just really magical. They like to share a lot of resources. And so that's kind of the basic concept there. We're trying to think about what we want to grow in our agricultural systems and then think about what types of soil life best partner with that type of plant or best support that type of plant life.
When you talk about that and you talk about what this idea behind the Johnson Sioux bioreactor and this whole idea of trying to promote the fungal communities, I'm always struck at how polar opposite that is from the current agricultural system we have, where we're really, we are mining the soil and then we're just going to replace that with more, whereas this is more trying to create that self-sustaining type system.
Yeah, that's exactly it. And, one thing that you'll hear a lot is peak phosphorus. A lot of people are really concerned about that. Phosphorus reserves on the planet are scarce, to say the least, and we're definitely kind of hitting that point where it's not easily mined, it's not easily sold, and that's true, even if it's not about scarcity, the cost, like fertilizer is always up and down in price, and just trying to replenish that pure nutrient availability to feed plants is kind of, maybe this is rude to say, but I think it's kind of an outdated way to think about how plants grow and to think about agriculture. And we're really changing our mindset to think about this, recycling, renourishing system where the plants are essentially feeding themselves. We are just tending the soil, trying to make sure that it's a good habitat, making sure that this livestock below ground, these microbes, these microorganisms can really thrive and they can reproduce. They have enough food to eat. They have enough shelter. They're not being disturbed. And then they're just kind of taking care of the plants for us. And so I think that's the new wave that everybody is excited about because it's a lot less work, it's a lot less money, it's a lot less stress, and it's just kind of, I guess I already said this, but it's just the way that nature does it.
So you have quite a bit of experience with it on your own. You're raising vegetables. Mm-hmm. Can you describe how much experience you have with it and kind of what's been your experience with the bioreactor system?
Yeah, well, so I've done a lot of variations with the bioreactors, in all honesty, working with Land Stewardship Project on this MDA grant to really put the fire under me to build the bioreactors to David Johnson's specifications. And so with this system, I've just been so in love with seeing the amount of fungi it's producing. We have a really heavy clay soil and we're pretty new to our farm, so getting started, it's just like clods of clay coming up. Within one season of using a bioreactor compost, we're seeing just so much more aeration, so much more activity in the soil. As soon as you start getting fungi, and we, with the vegetable system, we're using mulches too, so we have that kind of to our benefit. But it's just amazing how quick the soil structure starts to get built once you introduce this microbial inoculant. And I think the plants just respond in kind because it's again, this idea of the cycle. They're feeding those microbes, and then the microbes are feeding them. So you get these stronger, healthier plants that are more resilient. Just within one growing season, I've seen that in our own gardens just amazingly. It's just mind-blowing.
I get the feeling this is one of the first kind of big research projects we've done in this climate, because it was developed in New Mexico, much different climate situation. And I know it's been used, I think, in California too, a little bit. So this is a different climate. But yeah, talk about that and maybe some other barriers that we might have to something like this.
Yeah, the freezing temperatures is definitely the biggest issue. As you said, it was developed in New Mexico. It's widely used in a lot of drier ecosystems like Australia, New Zealand, California. All of the Southwest is kind of where the biggest research projects are going on. And they, I always read in them like, these bioreactors will be fine over the winter. And then you look at their winter and it's maybe one day just slightly below freezing. And so it's very different than our Midwestern winters. All my bioreactors freeze solid. Unfortunately, I don't have a way to keep them insulated, and so I've done a lot of thought about this and what it means. David Johnson, the discoverer of this method, says that they really shouldn't freeze solid for the best quality product. And there's a lot of people talking about this because it's kind of it's a huge barrier for northern climates. Like how, people don't have the infrastructure always to keep them from freezing. So is it that we just can't partake in using this amazing method, or, what do we have to do? So there's a lot of people that are kind of thinking about how our forests and our soils freeze, and the life in the soil gets by just fine. You still have fungally dominant ecosystems, you still have plenty of biological diversity, and so maybe part of it is selecting for organisms that can handle that freeze-thaw cycle. Others are kind of talking about how the freezing causes a lot of cellulose and the plant matter to decay so much more rapidly. If you've ever put, vegetable scraps in your freezer to make soup stock, if you let it sit on your counter for a brief period of time, they just rapidly turn into decay mode. And so that could actually be a boon to the biological diversity that springs up in the spring. So that's kind of the way that I'm thinking about it. I think we have to just adapt and accept this as how it's going to be. We're still seeing a lot of fungi. We're still seeing a lot of biological diversity. So it's really hard to know how much is getting taken away by that freezing issue, I guess I'll say, by our winter climate. And then in terms of other barriers and challenges, I think that the startup labor that goes into it is always, it's hard work loading these things. Like you said earlier, they're 6 feet tall, and so getting the right infrastructure and ladder setup that's safe and that can easily and quickly load them. Keeping them watered is always an issue, and doing the initial watering. I think a lot of people tend to use bedding or, bed pack, which in my experience, we have goats. It gets very, very dry, like hydrophobic, where it can take forever to try to wet it up the material. And so when you try to get this to 50 to 70% moisture content, you can be using a lot of water up front, and then trying to keep that moisture level going for a whole year seems to be one of the biggest challenges for a lot of folks. So those are kind of the main ones that come to mind.
I was just curious. I was looking up a little bit Dr. Johnson's on his website. What are some of the positive results he's seen with the producers he's working with down in the Southwest? I mean, what are they seeing yield increases, or what all are they, and what kind of producers is he working with, I wonder?
Yeah, I think as a researcher, he has a lot of different producers that he's working with. I think a lot of larger scale grain production and also hay in the West. I've seen trials with like alfalfa in New Mexico, where it's a desert climate and that's not something that would typically thrive, but they're seeing huge amounts of biomass, yield increases. There's groups that are looking at carbon sequestration and finding that this compost greatly enhances the soil's potential to sequester carbon from the atmosphere. Yeah, and plant, just in general, yield is one thing, but plant health and vigor is another, and just the disease resistance that is really coming from having this biological inoculant in the soil is really huge. So, and then, doing a deeper dive into the actual soil aggregation and looking at those soil communities, and just on all fronts, it's kind of like a miraculous thing where they're just seeing such great potential. Just the water infiltration and water holding capacity of the soil. And I think that is, again, why it's really a big thing for desert climates, because it very much increases that water holding capacity. so holding on to heavy rainstorms, not, reducing erosion and runoff, and that's largely due to the fungal content of the compost, but definitely critical, and especially with climate change and with our climate becoming more drought than flooding, it's really, I think, a very exciting thing for our fields that need that sort of support, and the fungal networking to hold everything in place. So that's another big benefit of this.
You have already been doing some microscope work. What are you seeing so far? So we've had, just to put it in perspective, we're not done with these yet. They were put in last June. We're sitting here now, getting toward the end of March. We're not even at a year yet. But you've already just looked at the 5 samples, mm-hmm. and I guess what are some of the things you're seeing, and I guess what maybe new questions that's raising as we kind of assess where we're going with this research.
Yes, I'm looking at them and taking pictures throughout the process to kind of get microscope pictures, 400 total magnification. So we're trying to just get a sense of what organisms are there, what types of fungi are we seeing, just from a very morphological perspective. And then we're also sending samples, like you said, to the U of M for genomic sequencing and to the Soil Food Web lab in New York. And they're doing some intensive microscope bioassays where they're counting total and active fungi, total and active bacteria, as well as all the different types of protozoa. They even do nematode analysis down to the species level, so they're able to tell us if we have any, pathogenic nematodes or any things that we should be concerned about. So those results are really exciting to see. We recently got the 6-month check-in back from the Soil Food Web New York lab, and some of the piles are fungally dominant. All of them have good beneficial protozoa counts. I guess by that I just mean that we kind of lump protozoa into 2 categories, either the aerobic flagellates and amoeba, or the tend to be more anaerobic ciliates. And so most of our bioreactors have a large amount of the flagellates and amoeba, and they have within normal reason amount of ciliates. So that's looking really good. The nematode counts are not as great at this point as I would expect. For 6 months in, the piles are pretty well aged, but we're still kind of hoping for more nematode diversity. And nematodes are a larger predator organism, so that's kind of the point of the 12 to 18 month lifespan. In order to have a compost that can really foster the development of those larger animals, like nematodes, which are really helpful in the soil, it needs to age for a long time. So it's not that strange that we're not seeing huge counts at this point. We're seeing some that are bacterially dominant at this point, or having indicators that they're becoming more bacterial. So we have a couple of little alarm bells like, oh no, what's going on there. But like you said, we're still halfway through the process at most, and so we're really curious to see how this next chunk of time, especially with it being spring, just kind of seeing what develops.
There are the good nematodes and the bad nematodes, because I know you talked about how, we've got some predatory ones, but can you clarify what people get awful excited about nematodes when they see them, and they show the microscope pictures and they see them squiggling around. It's like, I go, is that good or bad? And I'm never quite clear. But there is, like anything, there's good ones and there are bad ones. Can you explain that world a little bit?
Yeah, for sure. The nematodes are always fun because besides soil mites and the microarthropods, they're kind of the largest thing that you're going to see beneath the microscope. So it's always exciting when you do catch one. From kind of a very elementary microscope perspective, we can classify them into kind of different feeding groups. So we're either looking for bacterial feeders, fungal feeders, omnivorous nematodes, or the root feeding nematodes, or predatory. So the predatory ones are kind of the most exciting because they're the largest, and they're the ones that would eat the pests, like the little aphid eggs and stuff like that. The ones that you definitely don't want to see, obviously, are the root feeders, and they tend to thrive in the more anaerobic conditions and in poorer soils. So we're hoping that those aren't in our bioreactors. Predominantly what you do find are the bacterial and fungal feeding nematodes, the bacterial ones being the most common. And the interesting thing, I think Elaine Ingham has said this, I'm trying to remember where this comes from, but how the root feeding nematodes can reproduce super quick. That's why they thrive in soils, that's why they can take out entire crops. That's why they're huge agricultural pests. Whereas the predatory nematodes that we all really want to see, that are going to eat those pests, reproduce very slowly. They're a lot larger. It's kind of like if you think about mammals above ground, like rabbits are reproducing super quickly, just increasing their populations, kind of no matter what exterior conditions are like, versus the larger mammals like wolves that are going to take, they're having 1 or 2 cubs at a time. Are wolves cubs? I don't know. Pups. Pups. 1 or 2 pups at a time. Yeah, well, it's the same for those organisms below ground. So I just, when you think of those metaphors, it's like, wow, yeah, we need to be keeping our soils undisturbed. We need to be letting our compost age. All those things that foster the growth of the more slowly reproducing larger creatures.
One of the things that really struck me, too, about these systems is that they're scalable. You aren't stuck, because that's a big problem with agriculture. It's something that we deal with a lot with. If it's a new innovation or whatever, is it maybe doesn't make sense to buy this piece of equipment or put in this structure for just a certain size, because you got to make it, cost effective or whatever. But this, you can make, it's one of the most scalable innovations I've seen, from what I can tell anyway.
Yeah, I think that's really true on a lot of fronts. Like starting materials that you need to make the bioreactors, let's just start there. In order to make one, you basically have the materials to make 4 or 5. And so that in and of itself, a backyard person can make one and share the rest with their neighbors. A larger scale farm can make 4 at a time or more. You can load them. I load mine with 5-gallon buckets, and it is a full day workout. It's very hard. I think all of the LSP farmers, though, or at least most of them, are using the bucket loader on their tractor and making it go a lot quicker. So that's, just on the making side, it's definitely scalable. And then on the use end too, if you have a very small plot, like maybe you're just like a backyard gardener, you have 1/10 of an acre, you can use all of that bioreactor compost and spread it in bulk, all over the soil, or dig it into the soil, however you want to use it. Or if you have 100,000 acres, you can use little small quantities, make it into an extract and dilute it with various amounts of liquid. So it really can be used for any size operation for very low cost, and without much special equipment, other than when you do get into the liquid application, then you're looking at the sprayer equipment and machinery that can handle that sort of stuff. But yeah, that's kind of a great thing about it.
Am I right on this? Sometimes vegetable operations will use it for potting soil when they're getting stuff set up?
Yeah, that's because it is such a well-aged compost. It can pretty much be used straight up 100% as potting soil. I think it's good to include some sort of aeration, because with like any potting soil, it can become compacted if you're watering heavily. But I think Elaine Ingham has also said this about the compost that her organization, Soil Food Web, that they promote, which is actually a turned pile. But yeah, she says that she uses compost 100% as a potting mix and has had no issues, which a lot of people I think is kind of mind blowing, because you think, if you just go and buy a bag of compost and try to start seeds in it, they're probably going to rot, or you're going to have nutrient imbalances. But with these really well-aged composts, they're just like a very healthy, like forest type soil that is going to be beneficial for a lot of plants.
The on-farm research could be really fun, and a really fun way to do this farmer-to-farmer education. So is it just kind of fun to do something like this, I guess, and see what's going to come out? And also this is, from what I know, one of the few research projects being done in this climate. So that some really innovative stuff could be coming out, some kind of breakthroughs on whether this does work or doesn't work up here.
Yeah, it's so fun. I mean, my background is partially science. My major in college was environmental sociology, and so and it was a Bachelor of Science degree, so I count that. And so yeah, and I think that I love the science behind it. I love studying the microbiology, and I love that this method and just regenerative agriculture in general gets people so excited about the biology and about becoming scientists on their own farm or in their own basement or backyard or whatever. It's a simple microscope that you can use to look at the organisms. And I think that makes soil science especially a lot more accessible. You don't, like, chemistry was the thing that science was. It's chemistry and physics, and those are hard sciences to me. Like that was very challenging, and I don't think that I never really found that as interesting or as fun. I was just, when you think of the soil like that, it kind of makes it more dead and just kind of like something that's like very passive and something that is just a material. But looking at the biology and the diversity that is alive in there. It's like being any sort of ecologist and getting to look at different systems and how they work and becoming, I think that we feel like we also become more partners with the soil when we're looking at it that closely and really getting to know the creatures that are alive in it. So yeah, it's super fun, and the research is really important. Like we talked about with this winter climate and stuff, we're learning so many things, and I think that the different recipes that we're trying, it's just giving a lot of material and food for thought for lots of different types of farmers.
I kind of feel like the whole soil health movement was actually pushed by farmers. They were seeing things out on their own farms and actually approaching the so-called experts, in the institutions and saying, well, I'm seeing things like I can build organic matter, and the old textbooks always said you couldn't build organic matter in a typical lifetime kind of thing. So this is seems like one more step that where maybe the farmers, they have observed these things, they want to maybe take it away from it just being kind of happenstance and accidental, like, oh, great, I got this by chance, and kind of drive it a little bit more so they can rely on it.
And I just love that really, like, you've got your hands in the earth, like the farmer is at the end of the day the one who is doing everything. Like they have all these consultants and agronomists and fertilizer salespeople and all these things, but really, like, they're the ones that have their hands in the earth, that are working the soil, that understand how it works, and that want to make it the healthiest that it can be. So yeah, I think that's so true. It's so farmer led, and just all that intuition that farmers bring to it is incredible.
This podcast interview with Max was recorded in late March 2022. The research plan for the LSP Johnson-Su initiative calls for the current stacks to be torn down and the material they produce to be utilized by the farmers during spring planting. Another set of bioreactors will then be erected on the 5 farms, with their progress being monitored until the spring of 2023. Stay tuned for those final results. For more information on the Johnson-Su bioreactor system, see the podcast page for episode 271 at landstewardshipproject.org. There, you'll find a link to Ear to the Ground episode number 266, which features interviews with farmers who are taking part in LSP's on-farm bioreactor research. If you have comments or suggestions about this podcast, contact Brian DeVore at bdevore@landstewardshipproject.org, or you can call 612-816-9342. By the way, it helps us greatly if you can give Ear to the Ground a rating on iTunes, Stitcher, or whatever podcast platform you utilize. Thanks to Laura Borgendale, Western Minnesota musician, for Ear to the Ground's theme music. And a special thank you to all of Land Stewardship Project's members who make initiatives such as this podcast possible. If you're not a member, visit landstewardshipproject.org to learn how you can support LSP. Thanks for listening.